I'm Coby. I'm a team lead at ON Labs on the exploration team. So we're kind of like DevRel and product focused, and I'm going to share with you today some stuff about what we're building, and then we actually have a builder here who's going to share what he's building with our tools. So who are we at ON Labs? We are a blockchain company. We're making provable, programmable cryptography technology, so a lot of zk proofs. I work mostly on the ONJS SDK, and we have some other things as well. We built the Mina blockchain, and we're also working on an O1 VM. So we have a little bit of both, a little bit of circuits and a little bit of zk VMs. So Mina, kind of our most well-known product. What is it? It's the world's lightest weight blockchain. So it's basically a blockchain layer 1 that zk proofs transactions and keeps a state proof that's up to date without making network participants hold lots of storage at like an ever-growing rate. So it makes it easier for regular people to participate in the network. The succinctness using zk proofs makes it scalable and trustless, so easy for users to get involved. And it's powered by zk snarks. That's sort of the technology that enables this property. And just to sort of set the stage, I think people understand how Ethereum works. You submit a function and call data, and then the nodes in the network execute that function for you. And they agree on the output of the function, and that's how the network reaches consensus about state. But on Mina, what you do is a user will run their own proof, they'll upload the proof to the network, and the network simply verifies the proof and comes to consensus about that. So for a really cheap Ethereum transaction, there's kind of no difference. But where you get value is like a lot of off-chain computation rolled into one single proof with a fixed cost verification time enables some cool use cases that would either be really expensive with gas on Ethereum or maybe even over the gas limit completely. So we basically achieved this succinct blockchain, and with users running their own proofs, you also get these privacy and off-chain execution properties that are quite nice. And so let's explore ONJS. ONJS is a TypeScript SDK for writing zk circuits. It's quite easy, it's quite nice for engineering, zk aware engineers, I think. And the proofs that you write, the circuits that you compile with ONJS are sort of compatible with the Mina blockchain. So it enables programmable smart contracts in the zk blockchain ecosystem. What I really love about ONJS is that we say that it's literally just TypeScript. Take that with an asterisk, but it's compatible with all of your favorite kind of TypeScript tooling. Like we're leveraging this really mature TypeScript ecosystem and empowering zk devs to have that kind of tooling. And we have sort of a standard library for zk developers as well. From the zk circuit side, we have a lot of cool, we call them custom gadgets, like more high-level gates than just add in multiplication. And we have like data types that are useful for engineers, like unsigned integers. We have booleans, et cetera, so you're not just working with fields everywhere. We have Poseidon and native signatures, which I'll get into later actually, but it's a Schnorr signature over the pasta curves. That's our sort of signature scheme. And then what we also have more recently, which is really exciting, is more like foreign field arithmetic. So we can bring other types of cryptography into our sort of zk proof system. So for instance, we can do ECDSA and Ketchak, and we can sort of verify Ethereum stuff with Mina, which is really cool. And of course, we're building. So in the world of zk circuits, there's certain programming paradigms that people would like to have that are difficult to support. One common one that we get from developers is like a runtime lookup way of working, not just knowing exactly what your data will be before you get it, but at runtime accessing something dynamically. We're working on that. I don't want to give a date, but we're working on it. And then the other thing that ONJS ships with is protocol features for Mina. So it sort of natively knows how to interact with the Mina blockchain, submit proofs, update smart contract state. We have something called account updates, so it can sort of do balance transfers, and it knows how to speak to Mina. That's the thing. And zk program is what we call our abstraction for circuits. So I know that the code behind me is going to be quite small, but oh boy. But I'm going to get into like a really small code example, just sort of demonstrate how sort of easy it is to get up and running. So the example project that I wrote is like a signature verifier in ONJS, so you can prove that a given Ethereum signature is valid. My motivation for this is, in the past when we've given talks like this, we kind of keep all of our stuff in the world of ONJS and Mina. And it's cool, you can build something that talks to something else in Mina, but not a lot of people are on Mina, everyone's on Ethereum. So with this story that we want to tell about programmable cryptography, part of that is bringing the rest of the crypto world, and not just crypto, but Web 2 cryptography, into our zk provable world. So, like I was saying, the Schnorr signature over pasta curves is like what Mina uses, but Ethereum uses Ketchak, and SHA-256 is common, and there's these other schemes. So could we prove execution of one of those crypto schemes in ONJS? The next slide is going to be sort of the imports and just getting the classes set up for building a zk program. So we're going to build like a zk circuit using our DSL, and some interesting things that we've shipped this year are like a foreign curve and ECDSA and a bytes data type, and these types of things are all wrapped in fields, wrapped in zk in the ONJS library, but they're exposed to developers in like these nice high-level abstractions. And then the next slide will be this is like the declarative syntax of how we approach a zk circuit. So they have a name that's basically just used for debugging stack traces, but sort of critically they have a public input and a public output, and that's what's visible about the proof going in and what's proved by the proof coming out. And then it has a list of methods as well, which the next slide will be in greater detail. So, so the only method that this zk program will have, and it can have multiple methods. Each method is its own circuit, and then the program is a circuit that wraps the other circuits. So that's what the abstraction does for you. But in this case, we have verify signature. The public input that we defined earlier was actually the message, like the bytes that we're claiming have been signed. The private inputs in this case are the signature data and the public key that signed it. That's sort of an arbitrary choice, but it goes to show you that you as the developer can decide like what's visible to the public world and what's hidden from the public world, and you can prove the things that you feel like you want to prove and selectively reveal what you want to selectively reveal. And actually, it's quite a simple function. All we're doing is calling this method that we exposed by ONJS called verify ethers, which returns true if the signature is valid and false if it's not. So that's a zk circuit. And getting back to like leveraging the mature TypeScript ecosystem, what's really cool about this is that you can just write like vtest tests, or you can write jest tests to confirm that your circuits are behaving appropriately. So kind of the way this works is ONJS will run the TypeScript code and it'll test that, and if that passes, it'll move on to executing the circuit, which actually happens in like WASM. So the hardcore zk stuff is written in Rust and it's just exposed in TypeScript. But that will execute second, and if that passes, then TypeScript will say, okay, it worked. So in this case, we can generate a proof, and then we can expect that the proof's public output is true because it's supposed to be true. And it's quite easy. And then I would be remiss to not share with you the concept of recursion. So, zk circuits are really cool, and you can do this interesting stuff, and maybe it's quite easy to write in O1.js. But in order to make that work with more use cases, maybe more complex use cases, maybe things that need to be shared between different parties, not just one prover, we can add recursion. So in this example, I've added a new method, which is a base case, and I've changed the public output from a Boolean to an unsigned integer, which will be like a count of how many valid signatures have we verified ever. So the first time we run it in the base case, it will either return 0 or 1, depending on whether the first signature is valid. But then going forward, we can introduce the concept of a self-proof. So it's like a proof of the same shape as the proof that we're currently in, and we can verify previous proofs. So after you do the base case, then you can pass in that base case proof to do this recursive proof. So we call it verify signature again. The private inputs are the previous proof, the signature data, and the public key. And then basically the only thing we change in the code is first we need to verify the previous proof, then we need to access its public output, and that's the previous count of how many times we've verified the thing. And then we increment that, or we don't increment it depending on whether the signature is valid, and we return a new public output, and that has now sort of baked in both proofs, and we can keep doing that ad infinitum to maybe do more interesting, complex stuff. So kind of other use cases that we're interested in. Games. I think zk for games is really cool, especially in like a nascent developer ecosystem where you're not putting user funds at risk. You're not maybe putting too much stuff at risk, but you're having fun with it. zk identity and credentials is quite a cool use case that's pretty close. That could be a little bit more serious and interesting to like enterprise type things. DeFi and oracles. I guess the key insight there is like replacing signatures with proofs, but sometimes the proofs are just proof of signatures. So maybe there's just some scalability stuff there. And then rollups infrastructure. That's something that at Owen Labs we've seen a lot of people using our tools for. Not necessarily in the Ethereum ecosystem, but like infrastructure for Mina, because Mina has this, rollup proof aggregation technology built in. It makes it quite nice to build an aggregator and then settle to Mina. And then, just privacy stuff in general. Anything that can be done on chain with zk proofs, now you can sort of selectively prove that type of execution and share that maybe something is true, but you don't know who the participants were, or you know that a participant participated in something, but you don't know in which capacity they participated, things like that. And now I'd like to bring on Dennis from Astro Mina, one of our community builders, who is going to tell you about something he's building with our tools. Thanks, Dennis.
Thanks, Coby. So as we know, one of the biggest issues in crypto is interoperability, and with the emerging tech like zero knowledge proofs, we are going more towards the ping side, hopefully, and we have been seeing a lot of zkVM integrations with on-chain light clients, and recently Geometry Research, they basically integrated Celestia Blockstream on Mina, which enabled verifying SP1 RISC-0 gross 16 proofs on Mina, and we realized zkVM light clients could be utilized for having interoperability from Ethereum to Mina and basically enabling state bridging so that you can verify any kind of on-chain state data you want on Mina. And so ours is on the light clients and relay side, which is for now the most trusted side. And so the way, you can, and okay. So the way the state bridge currently we are implementing works is we just get a KZG plonk for the Ethereum's beacon chain state root execution, and we verify that on Mina with O1JS. And the way we verify it is using the work done by Geometry Research by converting the KZG plonk proofs to Kimchi proofs and having the Ethereum state root as a public output. And once a user wants to prove any kind of data they want from Ethereum to Mina, what they do is they just get a Merkle-Patricia tree of that storage slot, and they just reconstruct the Merkle root, and we compare it with the verified one in the circuits, so that they can verify their NFTs, fungible tokens, their proof of humanity, or any kind of other use cases like this. And yeah, thanks to the work done by O1 Labs, we are really looking forward to use especially O1 VM, because it will enable us to just generate proofs for each block, and then using folding schemes or infinite recursion, it will be possible to just have them in a single proof so that we can verify in a more optimized and efficient and performant way. Yeah.
Nice.
Thank you, Coby.
And yeah, that's our talk. Oh, hey, Connor. Thank you. Oh, questions? Yeah.
Thanks for the talk. Can you verify? You mentioned succinct or something.
Yeah.
What type of verifier does Mina have? Like, can you verify anything, or must it have been written in O1JS?
Yeah, so Mina's proof system is currently called Kimchi, which use pasta curves, Pallas and Vesta. So I would say it's pretty optimized for infinite recursion, so that it's kind of different from the other current proof systems. And this means the current app, the way you can just do conversion is the only way you can verify other proof system is just by doing conversion, and this includes SP1 proofs, RISC-0 proofs, Growth 16 proofs, and yeah, basically GNARC-based KZG plonks and also Growth 16.
So you could take a proof that Scroll is about to submit to L1 because they wrap in a Growth 16. You verify this proof in Kimchi, and then you settle on Mina.
Yep.
So you could technically have any VM on Mina. You could technically have kind of a infinite amount of rollups on Mina. You don't have to choose a VM.
Yep.
Yeah.
Okay.
And you can settle, for example, Kakarot as well to Mina. So yeah, but I would say proof conversion could be optimized, but it's possible for sure. Yeah.
Yeah. So I'll speak a little bit more on that. Specifically, what we're referencing is this work that was delivered by Geometry Research. They did some work for us to prove Celestia data inclusion on Mina, and part of that work is basically taking what already exists for proving things on Celestia, like an SP1 blobstream proof, and then they wrote the verifier in O1JS for that proof. So you would have to, for something other than Grot 16 or the versions of Plonk that this deliverable supports, you'd have to write your own. But of course, it's theoretically possible to write a verifier for any other proof system, like you can in Solidity as well.
And yeah, well, for Kakarot use example, for Celestia integration, they basically used SP1 with Tendermint Lite clients. So as you mentioned, Cat, Kakarot, EAT in your presentation, that could be also utilized in this way.
Yeah, I guess someone would have to write a Stark verifier in Kimchi, but I guess that could be
But Starks also could be wrapped to Snarks.
Yeah, true, actually. And also, I had one last question on your Lightbridge. How do you verify finality on Ethereum, the 12-minute?
So there are multiple approaches we take. So one of them is just from the beacon chain we just get the finalized blocks, and that's how we just verify BLS signatures. And also we are planning to just basically wait for a bit of blocks appended on that block to make sure double check. Yeah.
Thanks for the question.
Thank you.
Okay, that's super amazing. Is that all the question?
Yeah.
Okay.